Okay, thank you organizer for inviting me for this wonderful conference. And today I will talk about emergent critical fluctuation. I title little bit maybe change. Emergent critical fluctuation across a second order phase transition. So until now we have heard about lot about critical phase transition in various system, and we know the across the critical phase transition always associated with fluctuation, but most of the time we don't directly measure it, but we feel the effect of fluctuation in various thermodynamic or various response function. So idea of this talk is that to measure directly experimentally to critical fluctuation and see how their behavior across the phase transition. So this is a long collaborative project with Professor Bhautesh Bansal from Kolkata, and this is the first part of talk. And our let's me introduce our group. So we mostly work on the strongly correlated electron system in last few years, and then we are familiar with there are some topological materials, and there are intersection between two sets of materials, which some of them are topological host topological electric ground state, also long range order. And our goal is to in our groups to study this interplay of long range order and topology of electronic structure, for particularly in charges wave material and magnetic system. So we are trying to address the question that how symmetry breaking and topology together play a role in what kind of role play in phase transition. So as I said, most of the works done by students. So these are the students who are involved at various aspects of this problem, and these are the past students. Most of the work done by Kalimuddin, and this is the associate one of the Dr. Sudipto Chatterjee, who is now in Princeton. So today's talk, this work mostly done by these two guys. So as I said, to understand this problem of topology and long range order, we work various set of materials platform. One of the platforms is a quasi-only system, which is very interesting materials, is that its content, it's actually 3D crystal, but it is a chain like structure. So this blue is the metallic atom, and then surrounding are chalcogens, then they are each change closely bounded by silver iodine atoms and give the Van der Waals structure. So this is the overall this is a Ta Ac4 whole 2y. This is a composition of the system, but we have series of materials of this family, and to understand the physics of this material, we work with various collaborative theoretical as well as experimentalists. So as I said, this is a very interesting quasi-only system, and these are extremely narrow gap material. So some of them are shows metallic phase, like electrons can move freely along the metallic chain, and some of them are insulating gap. Then we have seen also some of this family members are superconducting, and definitely they show charge density wave, and we also observe non-trivial topology of electron structure in one of the compound, and one compound also shows ferromagnetism. So as we understand, this set of compounds shows very interesting phase diagram. And for example, let's say when you know that ferromagnetism, if you go below certain temperature, spin get aligned, give rise to net magnetism and ferromagnetic phase. So
battery is very low.
Oh, okay.
Connector
No, it's not my connector.
Oh,
Maybe
okay,
this
go ahead,
this you have to connect there. So then if you go above the transition temperature, it goes to parametric phase, which is a disorder phase. So driven by the temperature, we get to we get from, let's say, long range order ferromagnetic state to disorder non-magnetic state. And this is a shows this kind of phase transition, like a ferromagnetic paramagnetic phase transition, superconductor normal metal, and there are seemingly various kind of phase transition, and they follow similar kind of behavior. Okay. So, one of the interesting question we ask, what kind of, let us say, dynamics play a role across the transition, and what is their signature in the thermodynamic properties directly. So, as we said that, okay, it is not only electronic phase, even let us say if you consider, let us say, solid to ice phase transition is also follow similar kind of behavior. So, this is a very old well known physics, and one of the fascinating aspect of this phase transition is that, so you can categorize all these different kind of phase transition in few universality class. So, first order, second order, higher order phase transition based on this what kind of, let us say, order of Gibbs free energy shows the discontinuity. So, for example, although it is a maybe it can be, let us say, structural phase transition, or let us say electronic phase transition if you have a first order transition. So, all this kind of phase transition associated with the latent heat. If you have a second order phase transition where first order phase derivative of Gibbs free energy discontinuous, but second order derivative of Gibbs free energy continuous. Second order derivative of Gibbs free energy give the continuous, but exhibit discontinuous second derivative. The second order phase transition where you see that it is all the behave associated with this, let us say, large fluctuation with the transition, then definitely there is a higher order phase transition. And this whole classification is mathematically described by Gibbs-Landau theory, where one can see that across the second order phase transition, this order parameter, which is define the order of the phase, like a ferromagnetic, which is the ordered phase, goes to paramagnetic, which is a disordered phase, and order parameter can define your order of the phase, and free energy you can write in terms of function of the order parameter of the system. And then you can get or explain this all this kind of phase transition into various class of universality class. One of the main important question is that what is the order parameter in the system. So, for example, there is various systems or various transition is associated or order parameter like solid to liquid or gas phase, its density is taken as order parameter. For superconductivity, sometimes delta, which is superconducting energy gap, or superfluid density, which is present as a order parameter. If we look into this theory of second order phase transition, we can see that below Tc, which shows this kind of free energy functional, where there it has a finite value of the order parameter, which represents the order in the system, like a superconductivity in the material or magnetism in the ferromagnetic system. As you increase the Tc, order parameter goes to 0. Here is the following certain value, and one of the important things is that also at close to Tc, where you can see that its free energy landscape become flat. So, where little bit of noise in the system can enhance the fluctuation of the order parameter, and we can see that at t equal to Tc, order parameter goes to 0, at but fluctuation at the order parameter shows a divergence. Now, this is the textbook Gibbs-Landau expectation, we studied in the solid physics. Now, one can ask the question whether we can see it in the experiment or not. So, signature of this fluctuation we see it in various thermodynamics quantity like resistivity, specific heat, and many other, but direct measurement of fluctuation is not available. So, one of the reason is that this fluctuation window, if we estimate from the Gibbs-Landau theory, is quite narrow. For superconductor is of the 10 to the minus 3. So, that makes it very difficult to measure. So, our goal is to measure the order parameter fluctuation across this phase transition in this quasi-1D system. So, as I said, this is a quasi-1D system, or it is a 1D like metals. So, if we have a, let us say, 1D metals in the, so 1D metals generally susceptible to dimerization or Peierls instability. So, if you have a 1D chain of atoms, now if they are filled or half filled, for example here, so then it can lower the energy by dimerize this 1D metal chains and open a gap at the exactly half of the wave vector and this give rise to, let us say, dimerization of atomic chain, that give rise to long range order, which is called charge density wave, because charge become periodically modulated because of pulse instability. And this charge density wave is follow the similar kind of phenomenological modeling, and we can represent by exactly same two component order parameter of the as superconductivity, as we are familiar with this. But here it's little bit different, it's happened in the real space. So, where excitation in this charge density wave ground state is also, let us say, periodic excitation or travelling wave solution. So, actually one can have excitation in the phase and also one can have amplitude. So, excitation is phase called, let us say, Goldstone mode or phase zone mode, or excitation is let us say amplitude mode. So, then since it is a 1D atomic chain, one can have also, let us say, since you can have excitation is the phase. So, one can easily excite the phase at finite temperature. So, there is a theory called Wigner-Perelman theory, since you can easily excite the phase or you can introduce the phase excitation. So, it easily destroy the long range order system. So, in one hand, Payal's instability says that okay, you can have a long range coherent classical CDW state. On the other hand, Wigner-Perelman theorem says that you can easily destroy this long range order. So, there is a two competition. So, now what happens is that a real material is not exactly 1D metallic chains, it is a quasi 1D system. So, at T mean field where one can expect to have that CDW coherent state, but because of this quasi 1D nature, it don't it fluctuation cannot stabilize this or does not allow to stabilize this coherent state. But since it is a quasi 1D, this correlation rates start to develop along the perpendicular to chain. So, at certain point at lower temperature, interchain become interacting with each other and then establish the coherence long range order state at much more lower value than T mean field. So, what happens is that we get the CDW state at lower temperature, and this classical long range coherent state, when it transition from this normal metal to CDW state, it get fluctuation dominated because of 1D nature of the system. So, then we see that if we measure the resistivity, we see that broad fluctuation into this is in logarithmic scale, length scale, and this we can explain from this expectation from the Ginzburg-Landau theory. And there are other quasi 1D compounds also available, they show the broad fluctuation window. Now, we can here see that transition temperature compared to mean field is quite low, because 2 delta by kBT is around 3.52. So, all these quasi 1D materials is transition, CDW transition dominated by strong fluctuation. So, now what happens if you go to CDW state? So, for example, if we want to understand it, let us say try to understand from analogy from superconductor. In superconductor, this is a complex conductivity, and this for normal metal, this total optical sum rule says that if you integrate forward 0 to infinity, this real part of conductivity is given by this, and this n is the total carrier density and m is the effective mass. Now, when it goes to superconducting state, certain fraction below 2 delta condense into 0 frequency and give rise to superfluid density, and exactly this superfluid density give rise to your 0 resistance in the material. And in case of CDW, what happened is that since CDW is the classical periodic coherent state in real space, so a little bit of disorder it pin the coherent state. So, what happens is that all the spectral wave do not shift to 0 frequency, instead of it's shifted to at finite frequency which is defined by pinning potential, this phi 0. And this NCW which is integrated over piezometer give the NCW or superfluid, or let us say fraction of electrons condense into CW ground state. And here one of the interesting part, the NCDW is the pinned. So, instead of giving 0 resistance, it do not participate in the conduction. So, it do not give any conductivity. So, then it has a two regime. One regime where if we apply the electric field at low enough electric field which is below the threshold or pinning threshold voltage, this NCDW do not participate in conduction. If we have measured the resistivity normally determined by the N normal or normal part of the normal fraction of the carriers. Now, if you go above the threshold field, if we let us say apply electric bias beyond this pinning energy, then this coherence state can start propagate or start sliding up about the washboard potential and give rise to something called CDW current. So, we can by electric field we can go from let us say pin regime to different regime, and that is the different kind of dynamical phase transition which is which will be hopefully we will talk about Bhavatos in next lecture. So, rest of the part I will focus on this regime 1 where we apply very small electric field and try to understand this physics of this phase transition of CDW phase driven by temperature. So, as I said, this two fluid model total carrier density is sum of this in normal and in CDW, and these do not participate in the conduction. Now, if we measure the resistance of this CDW state in the CDW state, resistance is fluctuation in the resistance, it comes from fluctuation in the normal and fluctuation from the mobility, two part contribute in the resistance fluctuation. And since it is a low carrier density material, mobility fluctuation quite low. So, mostly it is a fluctuation due to this normal carrier part. Now, this normal carrier part is related to this also this charge conservation principle to related to the NCDW part. Now, if we go to deep below a charged wave state, this resistance fluctuation only determined by N normal, but close to transition we can estimate that this N fluctuation in normal which we can proportionate in CDW directly because of this total charge carrier is conserved in the system, and close to transition temperature which is proportional to this order parameter and directly proportional to susceptibility through the dissipation theorem. So, from this simple assumption we can see that directly measuring the resistance fluctuation we can directly map to order parameter fluctuation which is proportional to susceptibility. So, that is the conclusion. Now, we use the AC technique or let us say lock-in based technique to measure the resistance fluctuation of this quasi-only system using across the CDW phase transition. So, this is the actually out of phase part and this is the in phase part. We can see that background signal for us quite low. So, this is exactly matches with this 4 k meter almost matches with 4 k meter we expect from for sample, and this is a expected on by F behavior in the deep inside the CDW transition. So, as I said, this TC of this sample or let us say transition of this sample is around 263 Kelvin, where it shows the broad peak, and if we above this this is the normal state around 300 Kelvin, which is clearly see that this is a resistance fluctuation as a function of time. This fluctuation little bit weak, but as we go lower the temperature goes to close to transition, fluctuation become more significant, and then we go below the transition, fluctuation gets suppressed again. So, this is the power spectral density again of this time series data. We can see that at T equal to T c, which is a T CDW around 263 Kelvin, this fluctuation get enhanced. So, this is the exponent. You can see that above the transition this is about 1, and below the transition is 1, but close to transition exponent become 1.3. It is 5 minutes. Okay. So then we estimate the variance using which is noise power or fluctuation noise fluctuation, which is proportional to susceptibility. We can see that within this transition region, it follow the power law behavior. And then we estimated the fluctuation window. From this we can see that it is quite broad from this GL theory, and it exactly matches with this broad fluctuation window observed in our resistance fluctuation measurement. Then we did estimate the critical point from this power law fitting in logarithmic scale, and we get that around 263.03 Kelvin. And we can see that this is the reduced temperature we define by epsilon T minus T0 T0. Beyond, far away from the critical point, we can see that this exponent or of this resistance fluctuation is almost 1, which is for expected for mean field behavior. But within this very near to critical point is within plus minus 2 Kelvin, we can see this fluctuation strongly suppressed, and its exponent around 0.45. Then what we did is that we did the autocorrelation measurement and try to understand whether there is a relaxation, what kind of relaxation mechanism play a role. So we can see that autocorrelation follow the stretches relaxation exponential, and from this fitting in the exponential function we get the relaxation time scale of this fluctuation, and we can see that it also diverges, and this diverges we try to estimate of this exponent of this divergence of the relaxation time from mean field behavior. As I said, this is a travelling wave solution. So in mean field we expect that is softening of this mode is of the order of about 1.4 exponent, and experimentally what we observe is that this little bit away from the phase transition or away from the critical point mean field region, we get the exponent about on the 1.4 or 1/4, but near the critical point we again get the suppressed value is about a 0.5. So where fluctuation plays significant role. So then we did the correlation measurement, where we calculate the second spectra, and from the second spectra we see that away from the transition is almost broad, but at the transition point it is frequency dependent, and we can see the sigma is above the value 3. This is the exactly textbook expectation from uncorrelated fluctuation, which we should expect 3, but as a transition it shows large value, which says that it is a correlated fluctuation plays role. And this is a logarithmic scale plot, where we can see that away from the transition is 3, then if we enter the fluctuation region it start to enhance and become saturated. So and we enter the mean field to fluctuation dominated region. So then we see the diverging correlation, skewed non-Gaussian statistic, and low dimension plays critical role here. This is the work published here, and this is a take home message. So response of collective serotonins are encoded in the low frequency resistance fluctuation, order pattern fluctuation extended over an usually broad temperature window. Critical fluctuation diverges near TCDW, reveals critical singularity near TCDW, or let us say critical point anomalously lower values of exponent, which says that fluctuation dominated critical like weak first order transition, and exceptionally slow and non-Gaussian fluctuation appear within this small critical window. With this, I thanks my funding agency.
Thank you, Ritu, for the next talk. Yeah, questions?
Your second moment, it increases when you approach the transition.
Yes.
Then it does not come down anymore. It flattens to a value. Why it is
This one?
Yeah.
This? Oh, this is a reduced temperature scale. This is TC. This is this blue is the above transition, red is the No, blue is the below transition temperature, red is the above transition temperature.
Oh, I see.
So this approach the critical point.
Okay.
Further questions? Yeah, yeah.
Thanks, Nintu, for a very nice talk. For this 1/f spectra that you have shown, so I just noticed at around 235 Kelvin or something. So it was, I mean, there was small, it's possibly not completely 1/f.
Yeah. This one?
Right, so 230 Kelvin. So
This one is 230 Kelvin.
right. So I think there is a curvature signal there. You have any comment on this?
Okay, we have not checked it. I think there should not be any curvature, but we have not checked it.
Looks like there is not possibly pure proper 1/f.
Oh. So
The other question is, do you have any other lower temperature spectra?
okay, so around 100 Kelvin there is a transition. So we have not gone down. So we have okay, other spectra also there is no curvature. Okay, so from the fitting, although I don't know, because one is red plot on top of each other, most likely that's a visually it's looking like a curvature, but it's not there.
Any other question? Okay, I have a question. So this, so you are fitting this stressed exponential. I mean, why is that, and what is the exponential? So why do you expect that it's stressed exponential? I mean, is it really stressed or is it just exponential?
So we okay, so there okay, actually it's a little bit complex. Other dynamics also play a role. So we treated with, let's say, exponential form, but there are two type of. Okay, so there are two exponential components present in this mostly. So one is that coming from, let's say, relaxation of filter function and lock-in instrumental function. Another is associated with the actual fluctuation dynamics of this serial state.
Multiple relaxations.
So we have two relaxation. One relaxation which is quite low related to instrumentation, which is flat across the transition. Another is that associated with the transition. Yeah.
Okay, any further question? Okay, if not, let's thank Mintu again for a very nice talk. We'll move on to the next talk. It will be given by Professor Bhaptosh Bansal from ISAR Kolkata, and he will be talking about early warning signs of tipping point criticality around the charge density or deepening transition.